Recall from the previous videos that we had said that a regression line is used to predict a y variable from one or more independent x variables. Well, in simple linear regression, the regression formula is a single response variable, y, with a single independent variable or predictor variable, which we'll call x. And it's real simple to understand and conduct the computation. The next set of slides will demonstrate how the calculations work. Either Excel or any other statistical software will easily compute the values. And it's important to note that we will not have to do all of the calculations that we're going to use the Excel add-in for analysis to help us do that. And we'll have a separate video on that as well. Our focus, though, is going to be on a few key concepts. Number one, the basic linear regression formula, the coefficients, which are the multipliers of the independent variables to obtain predictions, the concept of residuals, errors, and that basically is the difference between the predicted and the actuals, overall performance of the regression formula in terms of how the amount of explanation of variance there is. Our whole goal is to have our regression formula explain as much of the variation in the response variable or the dependent variable as possible. So once again, our basic goal is to be able to draw a line through a given set of points that best explain the points to provide a prediction. If a line is good, a few things should be clear. First, that the line slices the data almost perfectly. Half of the points should be above, half of the points should be below the line. And the points should come as close to the line as possible. And we should have some consistency around the line. And what that means is that the points shouldn't start out close to the line and then begin fanning out. This graph over here basically demonstrates a little bit of that. We can see that the points do seem to have half above and half below the line, and for the most part, they seem to be pretty close to the line, and as well as there seems to be some consistency around it being up and down. You'll have a few a little higher and a few lower, but there's no pattern where it fans out or begins to curve downward or get closer to the line. Once we end up finding a line with a good representation, there are a couple things that we need to examine. The line we draw will represent what is called the fitted values. These fitted values are what the prediction formula believes the prediction will be based on a given x value. So for example, in the graph below, we can estimate that when x is 15, the y or fitted value will be approximately 10, and that's shown by the leftmost yellow dot. The next concept refers to the actual data points on the graph. Since we know that our line represents what we call the fitted or predicted values, we can examine the difference between the distance of the fitted value and an actual data point. And this point represents the error between the prediction and the actual value, and we call this a residual. So the concept of residuals and errors are the same. And it should be clear by looking at any one of these blue dots that the distance between the blue dot and the line, which is what would have been predicted for that same particular value, is considered an error. So the yellow dots will represent a fitted value. This value is estimated by the regression line and lies directly on the line. The green brace here represents the distance between the actual data point in blue and the red line itself, which would be the fitted value for the same value of x, representing the error between the actual and predicted value, and we call it the residual. Residuals below the line are considered positive residuals, and residuals above the line are considered negative residuals. The line that's created is a straight line, and we might remember that the formula for a straight line from high school math would be y equals mx plus b. If you recall, m is the slope of the line, and b is the y-intercept. The slope measures the rise over the run. How much is it increasing versus how much is it going across as a ratio. The y-intercept is where the line crosses the y-axis when x is 0. It's important to note that the regression formula will look very similar. And although there is a similarity, the letters in the equation are different, so we won't want to get them confused. So many textbooks will write the equation as y equals a, which is going to be our intercept, plus the letter b or beta times an x value. But the principle is still the same. We're just substituting different letters. So if we think carefully about our slope, it's the relationship between x and y. How much rise do we have in y over how much run do we have in x? And it states how much y increases each time we increase x. And the formula is a bit large, but the components can be broken down a little bit to something resembling our correlation. So if you see here on the bottom, B is actually equal to the correlation between X and Y multiplied by the standard deviation of Y divided by the standard deviation of X. So once we have the slope calculated, we can then calculate the intercept of the line by ensuring the line goes through the means of X and Y, denoted as Y bar and X bar. So using the slope formula on the left, we can simply rewrite the original equation and solve for A. A, therefore, is equal to the mean of Y plus B times the mean of X. And since we calculated B already, we'll be able to calculate what Y is. Once we have solved for B and then A, you can then use the formula Y equals A plus BX to calculate a predicted value of Y for any X value. So therefore, if X was, in this case, 15, we would end up with the value of 10 for Y. And the difference between the Y value and the actual Y, the predicted Y value and the actual Y value, is our residual. Now, as we mentioned, the error is the difference between the predicted Y value, which in many cases books will use the term Y with the little hat on it, and our actual value will be just Y. So therefore, in a formula base, the error will be denoted as E and will be the formula of Y minus Y hat. This will now give us errors for each of our predictors. But we would rather see how regression formulas and errors are overall. And so our goal is to create a standard error of the estimate. Remember that the standard error of the estimate is the standard deviation, in this case, of the residuals or errors. And we had calculated standard errors before about how far away from the mean these items were. So our standard error of the estimate is basically the standard deviation of the residuals and can be calculated as such. The standard deviation of the residuals is equal to the square root of the sum of each of the errors squared divided by n minus 2. Now again, we won't have to do this because Excel will do a lot of this for you, but if you want to know what's happening behind the scenes, this is the actual calculation. So we hope that the standard error of the estimate is small because 2/3 of the predicted Y value will be within one standard deviation of the actual values. Remember that 2/3 stands for about 66%, and we said that 66% of the data or 68% of the data will lie between plus or minus one standard deviation of the actual values. If the estimate is small, it means that many of the predictions are close to their actual values. So we want to get our estimate as small as possible, the standard error of the estimate as small as possible, because it will tell us how well the errors are. In Excel, we can use the formula STEYX, range X and range Y, to get a standard error between Y and X. However, we're not going to use this in our examples because the analysis add-in will calculate everything for us, which we'll see in our other examples. Now, if our regression formula is good, it means that our predictor variable will do a good job in predicting the Y variable. In addition, it means that as X varies up, Y varies in some manner with X, which we mentioned earlier is our covariance, and we could standardize to get the correlation. If they moved in perfect harmony, that would be great, but they don't. So X can predict some, but maybe not all of the movement in Y. If they did move perfectly, then the movement in X would have to equal the movements in Y, and they would essentially be the same variable. So generally, we want to get an estimate of how much this movement is related to or explained by our predictor variables. This value is called Rsquared, or the coefficient of determination. The number is represented as a percentage from 0 to 100. Low percentages mean the regression model explains low percentage of movement, while high percentages mean the model explains a large percentage of movement. So an R-squared of 0.22 means that 22% of the variance in Y is explained by the regression model. And then R-squared of 0.78 means that 78% of the variance is explained by the regression model. Now, this statistic is actually a fairly simple calculation, but again, we will not need to do this manually. Excel does this for us automatically. But suffice to say that the calculation is the R-squared is equal to 1 minus the sum of the errors squared over the sum of each individual response minus the mean of the responses squared. From the formula, you can see that the numerator is the sum of the squared errors, again to remove the negatives as well as to magnify the effect of larger residuals. The denominator is the sum of the squared difference between the actual value and the average or the mean. If our errors are small, then the numerator itself is small. And thus, we might get a value of 1 minus 0.01, for example. That would yield an R-squared of 0.99. If the errors we have are very large, then the fraction would tend towards 1, giving us 1 minus 1, which would be 0. Thus, the R-squared would be close to 0, and it wouldn't have any explanation of variance. So the variance in y, explained by the regression formula, is based on the errors, or the residuals. So here's a few concepts to know about this R-squared. High R-squared values does not necessarily tell you whether or not a model is good. And we'll see later why that's the case. But for now, generally, we're going to say that a high R-squared is what we're looking for. Low R-squared values are possible even though the model is a good one. Some behavioral sciences like psychology may have equations with a low R-squared, and it is perfectly reasonable or even accepted and desired. R-squared only measures the amount of variance in y explained by the regression model and should be interpreted as such. So when we talk about R-squared, we should say that 82% of the variance in y is explained by the regression model, or 65% of the variance explained in y is explained by the regression model. R-squared only refers to the whole model and not individual variable effects. And this is more important when we have multiple regression, which we'll see in the next module. Also, R-squared is not the only way we measure regression formulas, but for now, and for these modules, it will suffice. There's another term called multiple R, which is the correlation between the fitted values and the actual y values. R-squared is actually the square of this correlation. So in linear regression, we're going to actually do an example. We're going to use the data analysis add-in and easily compute everything for regression. The table below highlights in green the statistics that were discussed on previous slides. Using the table below, the formula can be created using the numbers that we have. The number of complaints is predicted by the refund requests. And this is an example of the output of using the regression component in the add-in in Excel. As we can see, and we've colored some of the fields here, even though they're not colored on the actual output, but the add-in will actually give us our regression statistics, and it will give us the multiple R as well as the R-squared value. And we can see the R-squared value there is 0.77. We're given our standard error and the total number of observations from this data set. We're going to jump down to the bottom, and we're going to see that it calculates the coefficients for us. And the coefficients there are 1.79, which is our intercept, and the beta for the complaints, which is 1.1759, which will round to 1.176. What we do is we take those values and we put them into our formula to get predicted refund requests. And that will give us, using the coefficients, 1.798 plus 1.176 times the number of complaints we have. And we can interpret this as every increased number of complaints, so every additional complaint will yield an increased number of refund requests by 1.176. Because again, if complaints was 10, we'd multiply that by 1.176. If it's 11, we'll multiply 11 by 1.176. So every additional complaint will give us 1.176 more refund requests. And that's how we would interpret this. Now, we're going to interpret a lot of these values more specifically in some of the later modules. But this is the result that we get, and this is how we handle our interpretation.